when you first break it, it doesn't hurt.
Yeah, when you first break a
No.
bone, it doesn't hurt, but as soon as you try and use it, it hurts.
Right. So
Yeah.
30 seconds. There's 2 questions here you should look at. And don't give me crap on the bottom one where you're like, I've never heard that. Well, then it's not the right answer. Okay.
Davidson, have you ever had an open fracture?
No, this arm got really close.
Really?
Like,
Like poking out, kind of?
yeah, you can't see very well, but like right when he put the blade in, my skin it like split. So I have like a Y because it was
Really?
so swollen.
Aw, stop. I actually have.
All right. How we doing? We got 10 seconds left. 5 seconds left.
Does anyone remember that basketball game where one of the guys like twisted his leg and then broke and then it was
Where? Oh, on TV. Yeah. He like jumped out and landed weird and like, ba-ding.
yeah, he jumped and then he like went like this and it just popped
Yeah.
out.
Yeah, it was right in front of him. Okay, here we go. Maximum number of double bonds the carbon atom can form is equal to
No?
2. Two double bonds. How about the number of double bonds hydrogen can form? None. 0. All right. Number 4. What do you think?
Yeah, it's definitely
E. Okay, paramagnetism, by the way, that comes when you have half filled P things. Then electron charge, sorry, that says change? That should say charge, which is ironic because I didn't type this. I usually screw up, the book doesn't. Electron charge to mass ratio, that is a thing, but it has nothing to do with what we're doing. Diamagnetism is when it's not. First ionization potential, not actually a thing. Electronegativity, that's what we're looking at. Okay, today we're going to do Lewis structures, which will expand with formal charges and exceptions to the octet rule. These are really important right here. Formal charges are as well, but I mean, you'll see these all the time. Formal charges, sometimes not. So here we go. This is all about formal charges. You probably, hopefully watched the video. You may have read it in the book, which I hope you have. But formal charges are used to determine the best Lewis structure when there is more than one valid Lewis structure. So carbon dioxide, we can draw it in 2 ways, actually. We can draw it where the O is double bonded to the C twice, or you can draw it where it's a triple bond on one and one on the other. Both of these are valid Lewis structures. They meet all the rules, but this one is wrong. And it's wrong because of this rule of formal charges. Okay, so you may want to take a picture of this because I'm not going to have it up long enough for you to write every word. So to determine a formal charge, for each atom, count the number of electrons in the lone pairs and half the electron it shares with other atoms. Subtract that from the number of valence electrons for that atom. The difference is its formal charge. Now, we generally only find, oh, that's not a true sentence. I'm not going to finish that sentence. You're a moron, Tom. All right. Permission to scroll lower. All right. The best Lewis structure is the one that puts the fewest, with the fewest charges. Meaning, and we'll see it with the example, but we want most of them to just be a 0. And the best one is if there is a charge, we want a negative on the most electronegative atom. So this is how, if we just look at these, this is what we're talking about. Formal charges, we know oxygen has 6 valence electrons, 6 valence electrons, 4, 6, 4, 6. That's the valence. Are we okay with those? But for formal charge, we're going to count the amount that are assigned. And that's what this is. These are the assigned. All right. So we didn't have these dots, but oxygen would have had its octet completed. So I'll put those for, so we're good at what we're going to do here. Okay, so what we do is we now calculate the formal charge on all of the atoms. So you count all of the non-bonding, so 1, 2, 3, 4, and then you take half of the bonding. So since there's 4 here, you only take 2 of them. Are we okay with that, sort of? All right, so it turns out we have 1, 2, 3, 4, 5, 6. If you just count a line as 1, then it's pretty easy. So we have valence and we have 6 that are assigned. All right, carbon, since there's 4 bonds, 2 each, we take half of that 8, or we just get 4. This oxygen, it mirrors that, so we end up with 6. All right, so if I take 6 minus 6, this has 0 formal charge. 4 minus 4, this has 0 formal charge. 6 minus 6, 0. So in this structure, there are no formal charges. All right, the bottom one, we have issues. So we do the same thing. We take, we still have 6, 4, and 6. Those are the valence. But now I count 1, 2, 3, 4, 5. So I have a 5 that are assigned here. I still have 4 that are assigned here, correct? And then here, oh, I should not have put a double right there. I'm sorry. I shouldn't have put that second pair. I have 1, 2, 3, 4, 5 here. Okay, so now I take 6 and I have a positive 1. I have 6 minus 5, I have a positive 1, and I have a 0. So 2 rules are violated here. First off, well, not violated, but this one's better because it has all zeros. Since this has 2 total charges, it's less likely to be the correct one. And then there's a super giant red flag. Oxygen can never be oxidized by carbon. All right. Oxygen, if this was a negative one, it would be more likely, but carbon can't make oxygen be a positive. We okay with that? Okay, so really, this is the proper picture for both of these rules. We never would make a very electronegative atom a positive. Okay, good enough. All right, so this is a test question that's very similar. The formal charge of nitrogen in NO3 is, now it already has this drawn for you. You do not have to draw it. You just have to figure out the formal charge on nitrogen. Will you talk with your partner through that problem? Ellie, do you have homework? Okay, if I ever give you a list and you have other things, your own, do those first. Okay. All right. Do we have an answer? Raise your hands if you think it's A. B, C, D, E. Okay, well, only people raise their hands for A. It is A, so that's good. We have 5 valence. Hold on. 1, 2, 3, 4 bonds, which means we take for a sign, and it equals a positive 1. Yes.
So wouldn't the 2 oxygen also be a +1?
For this problem, it doesn't matter, but we could look 1, 2, 3, 4, 5, 6, 7. So 6 minus 7, it's a negative 1.
Oh, so you take valence minus.
Yep.
Okay.
So this structure, it's actually pretty happy. Like we got some negatives here, some negatives here. 1, 2, 3, 4, 5, 6, a 0 here, and a positive on your central atom. Would this be a polar substance? This one would honestly be a nonpolar substance for a reason you haven't learned until chapter 9. This would be, yeah, but this particle itself, we could ask ourselves, is it polar or nonpolar? This actual substance itself would be nonpolar because of its structure. Even if it had polar bonds, I don't know, it's kind of complicated. Yeah, and these aren't real charges. They're like assumed charges of how they would have to act. And I don't know how to say it. They're not actual charges that exist. They're just a way for us to check if it really is the way we think it's going to be. Judah.
How do we know there's 5 valence again?
What?
How do we know there's 5 valence again?
It's family number.
Since it's in family 5,
You're going off of 5.
What?
You're going off of nitrogen to 5.
Yep, because it asked about nitrogen. Okay, so that's a super typical question. All right, so can you explain to your partner why, or any weakness of this Lewis structure? Look at it for a minute. What would a weakness be of this Lewis structure?
Wait, didn't we learn that like below like period 3 you could like put more electrons?
Yeah.
This one's weird because it's not, right? So
Yeah, and Murray just noticed something. Yeah, this is supposed to just be B. I don't know why I put a BE. That's just B. The answer will be the same, but yeah, it definitely should have been boron, not beryllium. I don't know how to, let's see. We're gonna hack this game. Oh, okay, it is working, but I'm so frustrated right now. Look at that, it never existed. You'll never know. Okay, so here is the problem. We'll go with that, Greg. It's all about formal charges. We got 7 valence, 7 valence, 7 valence, and how many valence? 3. All right, so we have 7 minus 1, 2, 3, 4, 5, 6, 7. That's solid, that's a 0. All right, I'll come here because it's the same as that one, 7 minus 7, so that's a 0. This one's 7 minus 1, 2, 3, 4, 5, 6. So that's a +1. And then we have 3 minus 4, because there's 1, 2, 3, 4. So that's a -1. So the gigantic issue with this is what? Fluorine can't ever be a positive. There's nothing on the periodic table that can, and I shouldn't have used the term oxidized because it's not really a removal anyway, but it's the same idea. Nothing can cause fluorine to be more positive and it more negative. It works the other way around. Mhm. Yep. So we're going to learn in the exceptions to the octet rule. This is a substance, but we just write it as B, F, F, and F, and we leave the octet for boron not completed, which is fine. Like, this is the biggest bully in the school. And this is like the 8th grader that clept out of 9th grade and is at school and he weighs 105. Like, fluorine can steal his lunch money all day long.
I like that other BFF.
There you go. All right. So we'll learn. This is the most common exception to the octet rule where we don't complete the center. Now that's coming up, so we'll see it again. All right.
You only like high electronegative things make it so that's possible.
Yeah, and really, really mostly just fluorine. Okay, this is, if you watch the video, this is where we're going to step in and talk about resonance structures. So this is like a new section, and we'll go quick on these. This is the Lewis structure we would draw for ozone. But what if I felt like drawing it with the double bond over here and the single bond over there? It's the exact same thing, right? So who did watch the video? Okay, thank you for watching the video. So this is the deal. The bond length of this and this should be different. This one should be long. This one should be short. But when you really analyze ozone, it turns out the bond lengths are the same. It is weird. And it's because electrons don't live in a space. They're moving around constantly. So a resonance structure takes into account that the electron can certainly be on this side of O or this side of O or the pairs of electrons. So a resonance structure implies, and it is observed, that the double bond is sort of on both and neither at the same time. That last little wiggle kind of got ugly. Pretty much the electron pair. And that's what a resonance structure is. So there's more of the same thing. So yada yada, this just says, but this is at odds with the true observed structure of ozone where both bonds are the same length. So, and we don't, it's not like they really do, but we assume both outer oxygens have a charge of -1/2 instead of one having a negative and one having a positive, or one being a 0. Okay, so it's the bond length that helped us to learn this. So a resonance structure is often drawn with a solid line and then a dashed line on both. We would not draw it like this though, typically, because that would imply just to the viewer that that was double bonded. So typically it'll be a dash or a segmented line. Okay, this is just saying somewhat the same stuff, but now we have, or I added this as an example as well. So one Lewis structure cannot accurately depict a molecule such as ozone. We use multiple structures or resonance structures to describe the molecule. So this one I last year I must have just switched here, but you could draw both. All right, or you can put the segmented line and you'd be fine. So when we have sulfur trioxide, go ahead, sorry.
You put the segmented line on both of them?
Both of them. So we have sulfur trioxide gas, not sulfite. All right, it needs a double bond somewhere. So really it could be in any of the three. If we were to look at the bond lengths here, we would notice they're all the same because the pair is moving constantly. So we would just add a dash, and that would imply a resonance structure. You can draw all three separate or one with dashes. They're acceptable both ways.
On the AP test, do we have to do all three if we choose not to use it at that point?
I don't know. It depends on the grader. It really, It doesn't matter that much. They're exactly the same idea.
Yeah.
Go ahead.
So is that why like graphene conduct electricity so well?
Why graphene does?
Yeah, how is it good? Like, sit on, like, made of carbon.
Yeah, well, it's not necessarily this exact same idea, but it's the idea of this word, which is what we were talking about, and that's that yes, the electrons are allowed to move. They're delocalized.
So they're not by the.
They're not locked in. Okay, so just as green is a synthesis of blue and yellow, ozone is a synthesis of these two resonance structures. All right, this is another way to draw it. It's not as common, where you just put a hat right here. And that's another way. But this is the least common, unless it's a ring. We're going to see a benzene ring here in a minute. And then it's really common to just see a circle inside of that. What's that? Oxygen? Oh, like it's an O. Well, the benzene ring would also have C's right here.
Don't they assume that you know that every point is normally a C?
Well, yeah, but then I didn't want to confuse him that I was just drawing oxygen.
Yeah.
All right. So now, in truth about these electrons, we kind of already said it. The electrons that form the second C to O bond and the double bond below do not always sit between a C and an O, but rather they can move along the two oxygens and the carbon. They are not localized, but rather delocalized. This is just a word you need to know from now on. A delocalized electron is usually an electron pair in a resonance structure that can really go wherever it wants. Now, make sure if you were on the AP test and they asked you about this, you wouldn't ever draw a third one, which kids definitely fall for this crap all the time. Okay, it's tempting because you're like, oh, the double bond can go wherever it wants on the side of the C. That seems to make sense, but remember, this is a violation that is so bad. Yeah, like if you did this on the front page of their AP test, they just put it in the one pile right off the bat.
Really?
No, not really. But they would want to. They'd be like, what an idiot.
It would change the perception of your answer.
Yeah.
Can you explain localized or delocalized again?
Yes. So localized would mean the electrons between C and H, they are sharing that pair and it stays between these two. Like it would be located in this part every time. Here they share one pair that are pretty much locked, but the second pair, since it could have been drawn here or here, in reality, it could also live in this region or this region. So since it has the ability to bounce back and forth, we call it delocalized. And it only happens on double bonds in resonance structures. Hold on, Cooper first, what?
So that's just all that is like a theoretical technique. To know delocalization. Both those are right.
Mm-hmm.
Those are good Lewis structures.
Yep. Okay, what, Reese?
Does it matter that the oxygens are like right by each other, or could they have been on opposite sides? Or is it just easier for the electrons to be delocalized when they're right next to each other?
Yeah, they would be close to each other for that exact reason. Okay. Now, the organic compound of benzene, C6H6, has two resonance structures. It's commonly depicted as a hexagon with a circle inside to signify the delocalized electrons in the ring. So it's a double bond every other carbon, and you can draw it both these ways, but you usually will just see it like that. Benzene's really, really bad for your body.
What does it do?
It kills your cells. These bonds break, and I don't remember exactly how, but then they screw up the function of the cells, and then you're no bueno. All right, don't worry about emptying those yet. I didn't get them out, so we can do that Monday. Thank you. All right. We good? Okay. this weekend, I've been trying the last couple of days to really, really get a grasp of the Pfizer vaccine and the Moderna. Is that the other one? And like why it has to be so extremely cold. And I've read about it. I've watched one little video. It's pretty cool. So on Monday, I plan to have it locked in so I can teach you chemistry that's actually super applicable.
I think it's crazy how it's literally like putting mRNA in your body to make your cells create a protein just like the COVID virus.
It's pretty amazing science. And it's not the whole coronavirus. It's the part that makes it the most infectious part, or in
The like spike.
the spikes that really are the ones that make it be able to penetrate a cell.
They're making so
We're not putting it in us. We're putting something in it that will trigger our cells to make it themselves. It's pretty incredible science.
it's crazy.
And you know what? This type of science has the ability to change medicine. And it honestly, if this crazy pandemic was worth anything, it will be the like 100 years of progress we made in vaccine science in a year. Like it's crazy cool.
So crazy.
The research and the money.
Yeah, they had so much funding going into it. Like,
In order to get on the good books for their 1.4 billion.
Yeah,
Hey, we're healthy.
it's awesome. Like, and when I say awesome, like I mean cool. I mean like literally like awe. Oh my, we did that in 1 year. This is ridiculously cool science.
How long did it take to make the polio vaccine?
A long time.
A lot faster when you're at
But yeah, the polio vaccine is a whole different process. This is like super easy compared to the old ones.
well, yeah, because they don't have to get like dead cells or like weakened cells. They can just make.
Yeah, there's nothing to grow. It's just chemistry. It's just lining up atoms in the right way so that they can trick your cells into making something to protect themselves. There's nothing cooler than that. All right. All right, we got that. All right, this is super, super important. Exceptions to the octet rule. Was this in one of the videos? I didn't watch them all. I just assigned them. All right. I thought I had them on there. Maybe I didn't. Exceptions to the octet rule, they're pretty commonly tested, so make sure you're kind of with me. There are 3 types of ions or molecules that do not follow the rule. So there's 3 exceptions typically. This one, as already written in blue, this one, I shouldn't say least important. It's the least common. So test-wise, it's the least important. But it's an ion or molecule with an odd number of electrons. Like that's just whack right there. If you have an odd number, you can't have a complete octet because everything's even. So like, how on earth? Why did they even let that happen? Well, it happens and it's fine. All right, next, ions or molecules with less than an octet. This is not very common, but we already talked about one of them, and we'll talk about the exact same one again. All right.
Was that just hydrogen and helium?
No, like the BF3 we had, that was one. But yes, hydrogen, if we did H to H, that would only have 2. Ions are molecules with more than 8 valence electrons, and this happens a ton. So it's the most common, but it's really also the easiest. You just throw them on the middle of the central atom and move on.
Unless it's above
Right. So that's what right here, when it says D and F, this cannot happen unless you have D or F shells available. So that's why in the video, it said family 3 or lower. All right. So we'll talk about each one. We ready? Take a picture of it. Okay. So, though relatively rare and usually quite unstable and reactive. Thank you, sir. Reese, you have an appointment at 1, which is in 2 minutes. And reactive, there are ions in molecules with an odd number of electrons, like nitrogen monoxide. It has an odd number. So we have 5. This is not there. That was just in a discussion. All right, we have 5 valence for nitrogen, 6 for oxygen. So that is 11. So when we put them together, oxygen will always finish the octet on it. All right, ignore this for a second. We'll finish the octet on oxygen first because it's the more electronegative atom. And then we leave the less electronegative atom hanging out there. We just can't complete its octet because I just don't have enough. So it has 1 that's just left over. Yes.
So that's to try to get like, electrons.
Absolutely, and that's what these things I scribbled out. That's why it was talked about. So we don't usually find nitrogen monoxide gas, but we can find NO-1 hyponitrate. It wants that extra electron to fix that, and so yeah, and then we would have that structure, and life would be good. So if this substance could find any metal to steal from, it would take that electron, become a polyatomic ion, and then hang out with the metal in an ionic compound. So they're extremely reactive. Good. Okay, fewer than 8. This is exactly what we talked about earlier, so we don't have to spend a ton of time here. If we have boron trifluoride, and we try to complete the octet on boron, it always gives boron a negative in the middle and a positive on one of the fluorines. That is not the way science works. All right, so instead of drawing it and completing the octet, we leave boron with only 6 valence electrons, but fluorine happily living with its 8. Yeah.
I just forgot, how do we determine what the central?
It's the least electronegative of them. Yeah. But it has 6 total now. So fluorine had 7, right? Boron gave.
So wouldn't it would just be stable because boron responds 3 times in fluorine.
Well, it needs 2 more, but there isn't 2 more. So that's why the exception is we leave it with 6.
Well, wouldn't it just go back like 10, just be like helium?
Go backwards.
Yeah.
Yeah, this will become like helium, very similar, but this is a non-metal, so it's not really losing, it's sharing to become like helium. So that's why we have it here. And notice we have not really drawn a Lewis structure for an ionic compound because they're not really a thing. So like NaCl, we don't really draw a Lewis structure here because we don't have to show where electrons are. We already know that they're around chlorine. And if we do draw this, some kids might think, oh, hey, we're sharing that pair. No, get out of my room. Metals, they gave. Okay. All right. Now, therefore, the most important representation of BF3 is this, not these. Fair enough. Okay, so here's the lesson. If filling the octet on the central atom results in a negative charge on the central atom and a positive charge on the more electronegative atom, don't fill the octet of the central atom. This really, really, really only happens here. I've never seen it tested anywhere except for boron trifluoride. It's absolutely the most one. So if you understand that, you should be fine. Okay. And then finally, more than 8, and this is really, really simple. If you get done and there's extra electrons, always put them on the central atom. So the only way PCl5 can exist is if phosphorus has 10 electrons around it. This is allowed to expand the octet of atoms on the 3rd row or below because we can expand it into the d orbital area. So if this number right here is ever more than 4, then you have to have an expanded octet. It's the only way phosphorus can bond with 5 separate things. It's okay. I'm glad you're excited. Oh. Good enough. So there's one very common one. This is common, but there's SF6. SF6, since this is above 4, well, we have to expand it. So we end up with S, then 1, 2, 3, 4, 5, 6. The F's just hang out. They get a full octet. I won't draw all those dots, but they just live happily ever after. All right. Yes. Has to be 3rd row or lower. Yep. Yep. Those are the top, then the 2nd row, then the 3rd row. And technically, the 3rd row doesn't have on here D or F, but if you remember, we did N-1 and it was 3D. Does that sound familiar? So it's sort of there, and especially in this, we're adding, so we really are pretending like we're going to the 4th row anyway. Kind of tricky, but I mean, it's weird how chemistry always sort of comes back and completes the puzzle itself. All right. So even though this is pretty rare, but whatever. Even though we can draw a Lewis structure for the phosphate ion that only has 8 electrons around the central phosphorus, the better structure puts a double bond between the phosphorus and the one on the oxygens. It has less charges. All right, it has negatives and zeros. They really never want to be a positive one. So, I mean, this one, I've never seen this tested, but it is an application of the same one. If you can simplify it by violating the octet rule, especially the lower you go, the better off you'll be. But this one's, it's not tested. Usually if we're expanding the octet, it's just a central atom that has more than 4 things on it. So don't stress too much about that. All right, so whatever. This eliminates the charge on phosphorus. The lesson is, when the central atom is on the 3rd row or below, expanding its octet eliminates some formal charges. Do so. Pretty rare, but you could encounter that. Okay. I have added a homework assignment. You probably saw it if you have your notifications turned on. Murray and anyone else, Soraya, uh-oh, she's asleep. This will go on your grade, okay? This will go on your grade. It shouldn't take too long, but I really, really want you to do some practice with Lewis structures. All right, so you just go to Canvas. It's in our module for chapter 8. The blue sheet, I probably have never put it on there. I can add it. So at the bottom, it was Lewis structure practice. You can just print this and then draw them. If you whatever, like to draw on your computer screen and you want to save that as a screenshot, that works too. And then you just submit it, either taking a picture of it or uploading your screenshot, same kind of idea. We okay with that? Soraya? Okay. You look a little tired. Have you swam the last 4 straight days it meets?
Only 3 days.
Oh, only 3. My bad. Okay, so these will give you practice. If you get stuck, look it up on the internet, not to cheat, but to learn. Okay. If there's one that tons of you get stuck on, text me. I'll draw it on my phone and put it into the screenshot or the group chat screenshot. Anyway, turn that in on Monday, and then we'll be good to go. I've had a super long 10 days. Okay, questions? This is what I want to do.